I'm about to eat this problem like Subway lunch. Problem 1824 minimum sideway jumps. Okay. So there's a 3-lane road of length n that consists of n plus 1 points labeled from 0 to n. A frog starts at point 0 in the second lane and wants to jump to point n. However, there could be obstacles along the way. You are given an array of obstacles of length n plus 1, where each obstacle's I, ranging from 0 to 3, describes an obstacle on the lane obstacles I at point I. Ugh, okay. If obstacles I equals 0, there are no obstacles at point I. There will be at most one obstacle in the 3 lanes at each point. Okay, so that means there's definitely a solution, right? Because if there's only one obstacle, I can always find a way around it. For example, if obstacles of 2 equals 1, then there is an obstacle at lane 1 at point 2. Okay. The frogs can travel from point I to point I plus 1 on the same lane if there's not an obstacle at the lane at point I plus 1. To avoid obstacles, the frog can also perform a sideways jump to jump to another lane, even if they are not adjacent. Okay, so you can jump to any lane below you or above you, right? Like if we're going from left to right, you can jump to any lane above you or below you, regardless of the fact that there's obstacles in the way, right? So like maybe you're at the top lane, there's an obstacle in the center lane, you can get to the bottom lane, you can just jump over it. To avoid obstacles, the frog can also perform a side jump. Okay, I already read that. Return the minimum number of side jumps the frog needs to reach any lane at point n, starting from lane 2 at point 0. There will be no obstacles on point 0 and point n. Okay. So in this problem, right, I guess it's optimal to go here. That costs 0. 1 side jump, 2 side jumps, output 2. Okay. Notice that we jump over this obstacle here. One side jump, 2 side jumps. Okay, interesting. I guess for this problem, you could think of it as a search problem. So let's build this graph out, this system. So it's a 3 by 5. Okay, so we'll do 2 for each. So 2, 4, 6. Oh shit, I lost the. Okay, it's best I'm gonna be able to do. Okay, so and then I'll just quickly. I'm doing too much here. All right, so I'm gonna draw the system as best as I can. I don't know why I tried to make the beginning so good if the remaining is gonna be so bad. All right, so we have the 3 lanes. Right, I'm gonna draw the frog. A lot of problems with frogs. I don't know if you guys ever noticed that. Looks pretty good. It's a pretty good looking frog. And then we got these rocks here. All right, we'll do blue rocks, whatever. So we got a rock here, and a rock here. Now, since this is a search problem, right? Our end state, right, is any of these nodes here. And we can think of this as vertices, right? If we think of each of these grid cells, right? Because we can think of these as grid cells, I guess. And, all right, so if I was to map these as grid cells, I don't know why I just messed that up so much. So let's map these as grid cells, but let's keep it looking similar here. Now, these cells you can't travel to, right? These are bad cells because these are the cells corresponding to the positions of the rocks. And your frog always starts here. Now, from any cell, you can go up or down or to the right. Right? Those are your options, right? Because you can sideways jump or you can go forward. I guess you could go backwards, but what would that give you? That wouldn't give you anything. So, from anywhere, what are the options that you can do? Well, you can actually side jump any number of cells, right? So from this cell, I could side jump here. And I could side jump here. Why did I do that? I could side jump here. I could side jump here. Yeah, I could jump here. Jump here. Jump here. Or I can go forward. I could also side jump here. Same for these nodes. So for any cell, I can't actually go forward here. I can jump here. I can't go to the blue cell, right? There's no path there. I can go down and go up. There's no jumping. Right? I can go sideways. I can go up. I can go down. I can go right. I can go down. I can go up. Hopefully I haven't missed anything because this is pretty complicated. Up and go down. I can go up. I can go up. I can go down. Okay, so these exhausted all the paths in this system, right? So I could model the graph like this and then run something like Dijkstra's algorithm, right? Because the thing about this graph, right, is that these paths have zero cost. So if I thought about the cost of using each edge in this node, in this system, right, this has cost 0. Anything going horizontally, right, to the next system of nodes has cost 0. While anything going vertically, right, if you have to do a side jump, is that what they call it here? Yeah, side jump, that's going to cost 1. So all these vertical edges, so all these arrows going up and down, they're going to have cost 1 associated with them. All right, and then I could just run Dijkstra starting from here and find my way through the system, right? So I'd start here, and turns out that the solution is, the optimal solution is to go here, then use this link, then this link, then this link, and this link, then this, I don't need to use that one, and then this link. And then if I sum the cost of these, right, this has cost 0, 0, 1, 0, 1, 0. So that's a total of 2. All right, so I have to use a total cost of 2 to traverse this system appropriately. But an even faster solution, right, because when you use Dijkstra, you're going to have to build the system, so there's going to be a lot of space. And then you have to use something like a priority queue to figure out, which vertices should I explore prior to other vertices to find the optimal path. But what could be even faster is to think about this in terms of dynamic programming. Now, you might argue, well, we can't do dynamic programming, right? Because when we look at the system, there's obvious cycles, right? Like, the issue is when you have dynamic programming, what we would like to see is something that doesn't have cycles in it, right? We want to have a kind of, I want to say indicative, right? But we want to have this kind of synchronous, I don't know. We want to have this approach where we can solve for one state, right? Synchronous in terms of I solve for one state prior to solving for a subsequent state, right? There's a natural order. And if we wanted to think of this in terms of dynamic programming, right? When we look at any node, so if we had, let's just say we looked at 2 different columns, right? If I wanted to solve for this node, what would be optimal for traveling to this node? Well, what are everything that could travel to it? Well, this can travel to this node, and this can, and this can, right? So in order to solve for what's optimal for this node, I would need to solve what's optimal for the previous node, which isn't dependent on this, so that'd be fine. And I'd have to solve for this node. Well, in order to solve for this node, I would have to solve for this node, but what can also go into this node? Here. So in order to solve for this node, I'd have to solve for everything that goes into that, right? So I'd have to look at this, and also this. But now I have a cycle, right? Because in order for me to solve this node, I have to look up here. But in order to solve this node, I have to look down here. So it's not completely, obvious that you can use dynamic programming in this problem. And the way of which you can do that is by addressing the manner in which you draw these edges. So reassessing how do I draw these edges in a way such that this can be modeled as a graph that is solvable using dynamic programming. So I guess the first thing you can note using this system here as an example, ultimately from any spot, I guess the first thing you could think about to change the way you model this problem, instead of modeling it in this convoluted mess, you can think of it in terms of the previous state and the cost to get from the previous state to the current state. So I'm going to just move this down, and maybe we'll look at it later just as an exercise. I don't know. And let's redraw this graph using a different idea. Okay. One that is modeled as a DAG. Now, going left to right costs nothing. And going vertically costs 1. Now, from any state, how much would it cost to get to the next rows, the next column's additional state? So from any state, let's say if you could go here, you can go here, here, or here, right? From this state, you can go here, here, or here. And then finally from the bottom state, you can go here, up to the center one, or to the bottom one. Right, so this is a different way of modeling this problem, saying, okay, what are the ways I can get to this top state, where I can get it from going from this top state, from this bottom state, or this bottom state, and what would be the cost associated with it? Well, if we look at this top graph here, so we can repeat this for the remainder of the graph, I'm not going to do that, but to get to this state, I can get there using the middle state, the top state, or the bottom state. To go directly from my left, so to go from a left state to me without having to cross any vertical boundary, that has cost 0 associated with it. Right? There's 0 cost going from here to here. To use the bottom state, built into this edge is the fact that I'm going to have to go to the right and then up. Right? In order to use this diagonal edge, I'm going to have to go to the right and then go up. Going to the right costs 0, and then going vertically costs 1. So the cost of this edge is 1. Now you can make a similar argument for this system here, going to the right. Right, you go to the right and you go down. But the difference here is that there's a block in the way. So since there's a rock in the way, I can't actually use this edge, right? So that edge would have infinite cost associated with it, right? Because in order to get to this state from this state, right? I guess technically I could go down and go to the right. But if I can go down and then go to the right, I might as well just go to the right. Right? So I don't need to consider the fact that I could go down and then go to the right. Only going, right? Because the only ways to get to this state, I guess the point I'm trying to get to is, right, is like, you could technically say that, this person doesn't have to go to the right and then go down. They can also just go down and then go to the right. But if I go down and go to the right and I can make it, I might as well just use the path that ends here prior to the one that ends here. So I don't need to consider this path if I have a path that goes to here. Right. So if I want to use this path and go down, if there's a rock in the way here, then I can't use this path, right? Right, if I'm looking here and I want to ask, can I use this path here? Well, there's a rock in the way, so I'm not going to be able to use a vertical path like this with cost 1. Right? I'm trying to think about this fact of going down and going to the right really quick. If that's not going to be an issue. If that's an issue or not. Go down, go to the right. If I can go down, then I can go to the right. No, yeah, it's the same thing, because then I could definitely use this path. So basically this problem now can be modeled in this manner here, which means that when I do try to run dynamic programming, you'll notice in order to solve for this problem, I only need to look at this previous state, and this previous state, right? In order to solve these previous states, you would look at previous states before them. So there is no longer this cycle issue, right? This cycle issue no longer exists because the system is modeled in a slightly different variation, right? So in order to solve for this green node, I'd only need to solve for these 3 previous nodes. And then just determine if these edges exist, right? The cost of these edges, well, since this is the same this would be cost 0, and these would both have cost 1, depending on the value here. Right, if the value here is a rock, then you're not going to be able to use this edge because this edge is going right and going down. Right. And it won't be the case that you could use this system going down. Or would that be the case? Sorry, this idea is still very much so confusing me. If you're here, you can get here going this way or this way. So yeah, I don't think that matters. So if there's a rock here, I don't think it really matters. As long as there's not a rock here. If there's a rock here, then this will have cost infinity. Okay. So let's go ahead and solve it. I'm not exactly sure, but it's fine. Okay, so we'll set this D array to be 0, 0, 0. Actually, 1 will be the first value, right? Because you start, wait, this is flipped. You start in lane 2, right? So the cost to get here would be 1 because you have to go 1 up. And the cost to get here would be 1 because you have to go 1 down. And then you'll look at each column. And you'll start at 1 and you'll go to the length of the obstacles. So how far it takes to get to the end. And then we'll create a new D, 0, 0, 0. And then we'll look at each of the nodes. So range 3. So the top one, the middle one, and the bottom one. So 0, 1, and 2. And we'll say, okay, well, the cost to get to this node, J, equals the minimum cost to get to any previous node that can reach you. So, okay, so that'd be D of K. The weight of using that node for the weight of the node and the node in, well, the weight to use to go completely horizontal would be 0. And that would occur for the same row as J, right? So when we're looking at this system here, right, the cost to go from here to here, if the J was 1 and the previous node's value 1 would be 0 versus the other one would be 1. So 0 in J, if you use a value greater than J, it would be 1 and J plus 1. And then similarly, it would be 1 and J plus 2. So I'm just looking at each of the nodes, and then the weight would be the cost of that node to get to me, right? So this is a vertical one, and this is a vertical one. So maybe we should do K mod 3 to keep it within the boundary. Then we'll take the min of that. So that's what the cost would be. And then at the end, we'd say, well, if there's an obstacle at the current node we're looking at, so if it's greater than 0, that would mean that new D at, because it's an offset of 1, right? Because if there's a obstacle in the 0th position, it's at 1, so I'd subtract 1 from it. We'd set it to float infinity to say, no, you can't actually use this track. And at the end, you just say D equals N of D. And then you return D. Oh, return the maximum. Oh, wait. The minimum cost to get to D. Okay, so this is 0. It's obviously not right. Okay, so let's print out D after each iteration. Just to debug here. Do a little debugging. Alright, so it's 1, 0, 1. You can't get here, so it's infinity, 0 and 0. To get here, it's saying the cost is 1, but that's not true. Because in order to get here, you have to use this path. And there is no way of getting there using 1. You'd have to go down, down, and up. So yeah, the idea is true. It's float infinity if so you look at each of these and you'd say, well, if what? If D of K mod 3 not equal -1. Not -1. So if it doesn't have the rock in the way, right? So because you can't get here because there's a rock in the way. Not if D K minus, it's just K minus 3. I don't know what I'm doing here, guys. One, 0, 1, infinity 0. How is this 0? This should not be 0. Right, the cost to get to this one should be 1. Oh, I did for ranging 2, there's 3. Now I'm getting a feeling that this is going to error out, so let's just leave those for another day. All right, cool. There we go. All right, so time and space. Well, for, say, n equals length of obstacles. All right, for time, well, we have to look at each obstacle to make a decision, and for each obstacle, we have to look at 3 of the previous. Well, really 9, right? Because for one node, we have to look at all 3 previous nodes to make a decision. So 3 times 3, that's 9. It's still constant. It doesn't scale with the length of obstacles. So that's just big O of n, right? Because we have to look at each n obstacles, and then we do 9 operations for each 9 operations total. So O of 9n, that's just n. And then for space, well, we make this a size 3, doesn't scale with n, and then we just keep creating a new d of size 3 and then updating it that way. So in total, it's always going to just be size 3, so that's constant space. And then with that, you have the solution, O of 1. Okay, cool. Thanks, guys.